Hey there viewers, uh, like you can tell it's Mixy91 and welcome back to Gameboy and Gameboy color hacking tutorials, and today part 8. And I've got this text document open where I have pre-planned what to tell about today, and I'll be explaining program counter a little bit better, although I have given the specific idea about it already. Then we check what stack and stack pointer mean, and you can see that, well, program counter tells where the next instruction that is executed is located. So that's part of the CPU or the processor for telling where to load the instruction from memory for some registers to use, and then we can execute the instruction that is loaded from the memory. And program counter is pointing to a memory address where we pick up the instruction to be executed. And it's not really important to know how this works better than that. But then there are well, yeah, I'll be going on these one after another, so you'll be seeing, you'll be hearing more about this soon. So we check about stack and some machine instructions: push, pop, call, rstay, and ret. We can which all modify the value of stack pointer. These have that in common. They all modify the value of stack pointer. And also, well, they all modify program counter, but especially these two. After that, I'll be explaining what tables are and how you point to certain values in certain indexes of the table. So we could, for example, think that we have that moveset and evolution data for each Pokemon, and it's the data is pointed from a pointer table where we have 16-bit values or 2-byte pointers to each evolution moveset data. So, for example, we could say that Bulbasaur's index in the table is 1, Ivysaur's 2, and so on. And how we can, well, how can we work out with tables and by knowing certain indexes and such. And another thing that related to this is, does a value belong to a restricted table? So we could build our own table and check whether, for example, the current value in register A matches with one of the values in the table, and if it does something and such. And then I'll explain how to copy data, because this is a really useful operation and it's not that hard either. It works actually with a simple loop code. And then I'll be explaining subprograms a little bit better, and these all have to do with calling. And then we check some original in-game routines, and also introduce you to Lin's tool, the same person who has created this Johto map, called Gameboy Assembler Plus, which is actually better than, well, it's in many ways better than the normal assembly editor, which actually it doesn't know how to assemble data. This is an assembler. It's not an assembly editor. There's a difference. But yeah, I'll just open this tool, the assembly editor, and some ROM file. And here you can see the ROM data on the left, and the assembly instructions that match up with the ROM, with the code on the right. For example, F3 matches to DI, which is an instruction that disables interrupts, and those will be explained later. And this is jump code, for instance, and such. Well, I'll just track down some original routine and start explaining stuff here. For example, well, here we've got a certain routine. You can see that here is this return instruction. So this code right here at 0024FE is, well, some other routine either calls this, or there is a relative jump code to this routine, or a normal jump code. But that's how it works. And on the left here, you can see the value of program counter when this instruction is executed. So when the CPU starts executing data here, the program counter is set to this address, or the pointer value here. This is like the ROM bank and the pointer, but the pointer is in a more readable format. This is called Big Indian format. So the way you write it in the ROM would be FE24, which is a Little Indian format. Just like I have explained, to write pretty much every pointer in the game. They're all Little Indian, but this is Big Indian format. The bytes are in the other direction, in a more readable format for human. And so PC is first set to 24FE when we start executing data here, and then the CPU does something, and what it does is to, well, it brings this byte E5. It brings it from the RAM memory, or the in this case ROM memory, because we're in ROM bank 0, which is 24FE. It brings this E5 from this ROM address for the CPU to use, and after that it increments program counter once, and then program counter points to this address 24FF. Value of program counter is 24FF. So next time when it starts executing another instruction, it knows the load data from ROM in this address instead of the E5. It knows how to load CD along with 50 and 25 due to some mechanism which I really don't know about either much. Well, yeah, that's pretty much about program counter. So it always points to the next instruction that is executed, and after that instruction is executed, it is incremented. So it points to the next instruction, and in this case, program counter is incremented thrice because it can't point here or here, but it has to point here. So it knows how to load the next instruction from memory properly for the CPU to use. And well, let's see. I'll start writing stuff here. So stack. Before, when I introduced the specifics of the different parts of RAM and ROM you can access with memory viewer, I told that the work RAM area is between C000 and DEFF, and at E000 we've got the echo RAM that echoes the data of the work RAM between C000 and DEFF, and in this work RAM we store all the information we need to access at the time, just like party menus, the specifics of the wild Pokemon encounter and whatever. And then we've got the video RAM, save RAM, input and output part of the RAM memory. This is actually used for stuff such as registering the button presses. When you, for example, press A button, the game knows what to do. And here we've got the high RAM area. But after DEFF, we've got this 100 byte in hexadecimal. So we've got 256 bytes in decimal. This area right here, starting at DF00 and ending at DFFF. And if I set automatic update on, you'll notice something you could think this is cool. You can see that there's lots of stuff going on in here, and the bytes change rapidly into each other. And this is because all the time, when you can see what is happening in the screen right now, well, in the background there's lots of code going on, and at this time the CPU is using these push, pop, and call instructions, and maybe something more. It is actually doing a lot more than these, but it's using push, pop, and call instructions, and write instructions too, of course. And with those, it's modifying the bytes you see here. And this area between DF00 and DFFF is reserved for stack. And stack is a memory area that is used for making it easy to save register values for further usage. So we could, let's just say that we, for example, want to load A with the value of D004, do something with A, and for example then load A in. Well, we could, for example, put A back in D004. Yeah, let's just say we want to do that. But before this code, let's just say that A had the value. The value of A was first 40, and after the code, A has the same value as D004 because it was put there. And this could, for example, be 22 or whatever it is. But after this code, we could actually require that A still has that value 40. And if we wanted to do that, we would, for example, have to load that value of A into register B, so B has the value of 40. And then load the value of B back to A, and then we have 40 in A again, which is fine. But also now we've got a problem, because now we have modified register B without possibly having not wanting to do that. And we could, for example, yeah, we could always do something like, we could load, let's just say we want to load A for further usage in D000, and then we can load D000 back to A again. And if we do this, the value of A won't change during the process. But if we want to do lots of stuff here, we may have to use all the registers during the process. And so all of them will have to change, and all the registers have to be stored somewhere in RAM. And this is not convenient. It takes a lot of space just for keeping the values of registers safe. But for this, we have stack. And stack is, like I said, it's a memory area where registers are saved for further usage, and this saving can be managed with push instruction. And how it works is that all the time, well, this is actually a bad example. I can show it like this, but let's just say that, well, the stack pointer, it tells where the top of this stack is located. In this case here, well, I can't really see where the top of the stack is located. But what I can see that the stack pointer is smaller, or actually in this case it's bigger than dfc8. And when, for example, changes data here, the stack pointer points here in dfdd. And, well, as an example, let's say that our stack pointer has the value of dfdo, and then we have register A has the value, well, register B has the value of 30, and register C has the value of 40. So in this case, BC has the value of 30, well, 30 and 40, yeah, 3040. And if we want to save BC for further usage, we can use push BC instruction. Push works so that you can push any register pair in the stack, AF, BC, DE, or HL. And this is actually the only case, push and pop, where AF is used as a register pair. BC, DE, and HL are used a lot more often, especially HL. But we can push BC into stack. Not into, onto stack. We can push BC onto stack. And this means that... well, let's see. Yeah, I think if we do this, after this command, stack pointer has the value of dfce, because this push BC, it stored values 30 and 40 onto stack. And what I mean by this is that it stored, well, I don't know if it stores B first and then C, or first C and then B, but anyways, stack pointer has now been decremented twice. So its value has been subtracted by 2, because we pushed 2 values, 30 and 40, on the stack. So dfdo 30 to dfce. And now the values of dfdo, dfdo are 30 and 40. This is what push does. It pushes a 16-bit register value on the stack, and then it decrements the stack pointer by 2. And after this, stack pointer wait a minute. No, now I'm telling this wrong now. If stack pointer has the value of dfdo and we push BC, stack pointer indeed turns in dfce, but the values of dfce and dfcf are 30 and 40, because now stack pointer points to where we pushed BC. Well, yeah, stack pointer points to dfce, and in dfce we have this 2-byte value, 30 and 40. And now we can pop BC from the stack, and after doing this, BC has the value of 3040, because these 2 bytes are popped from the stack and brought into register pair BC. So BC has the value of 30 and 40. And with the pop instruction, stack pointer is incremented twice. So stack pointer is dfce plus 2, which is dfdo. This is what push and pop are for. Push pushes 2-byte value on the stack and decrements stack pointer twice, so that the stack pointer points to that 2-byte value that was pushed there. And pop instruction pops 2 bytes off the stack and increments stack pointer twice, so stack pointer points to 2 bytes ahead, and this 2 bytes ahead is where the next part of the stack that has to be popped off is located. Let's see, as an example. We have a routine. We want to keep the value of BC the same. So we first we have stack pointer set to dfeo. And we have A has the value of 30, B has the value of 51, C has the value of OF, H has the value of 70, and L has the value of 03. Yeah, let's start off with this. And so now A is 30, BC is 51 OF, and HL is 70 03 as register pairs. And if we want to keep the value of BC the same, we push BC on the stack. And after this, BC still holds the same value. What we did, we copied that value on the stack, and stack pointer has the value of DF, DE, because stack pointer was decremented twice. Now, if we, for example, want to, well, I can't think of a good example right now. I'll actually make it so that B has the value of 0, 0, and C has value of 0, 2. This works better. And after we push BC, BC still has the same value, 0, 0, 0, 2, and stack pointer is decremented twice. And then we, for example, load. Let's just say that we also want to keep the value of A the same. So we first push AF, because we have push works so that you push a 2-byte register pair, which is AF. So we have to push 2 bytes. We can't just push A, we have to push AF. So AF, we don't really need to know what the flag register has as value. A is still 30, and stack pointer is decremented twice. And when we push BC, stack pointer is still decremented twice. So from DFDE, it's decremented to DFDC, which is DE minus 2. And now, after we have pushed AF and BC, I'll just express the values of stack pointer a little better here too. So let's just say, first we pushed AF, then we pushed BC. So BC is now on the top of the stack. So in starting at DFDC up to DF, FF, we have 0, 0, 0, 2, which is the value of BC. Then we have 30 XX, and X here is the value of F register, and some other data that follows it. This is the case after these two instructions. And after we have pushed BC, we for example want to load well, a register won't be needed in this example, but I'll just leave it the way it is. We for example want to do this. We add BC into HL twice. This is actually somewhat related to the table examples I'll be showing off soon. And after these two instructions, HL has the value of 7007 because this was 7003. We added 02002 twice. And then we, for example, want to load a register with the value of HL. And now A has some random value, whatever was stored in that address. And then we, for example, want to store A into RAM address D150. So we can do this. And now D150 has the same value that was in ROM address, or the address 7007. And after this, we want to pop BC and AF from the stack. And you can see that the first values on the stack are the values of BC. So we first have to pop BC, and after doing this, when we pop BC, stack pointer is incremented twice. So SP BC has now the value of 0002 because this was popped off the stack. And stack pointer has the value of DF DE because it was incremented twice from DF DC to DF DE. And now it points to instruction. It points to the value of register per AF. And now if we pop AF from the stack, AF has the value of 30XX like we wanted to, like from the start, that was the value. And stack pointer has the value of DF EO. And this is how it works out. We have a certain address. A stack pointer points to a certain address in the stack. Well, it points always to the top of the stack. When we push data to stack pointer is decremented to point to that pushed data. And when we push data again, stack pointer is incremented again. In Gameboy it's always incremented twice because we always push 2-byte values. And then we want to pop them in this kind of order. Then we pop BC from stack to make BC hold the original value, and stack pointer is incremented twice. And then we pop AF to make AF hold the original values, and stack pointer is incremented twice again. So after these operations, we have HL is modified from 7003 to 7007, and the value in 7007 is stored in RAM address D150. This is what this code does. And the interesting thing to note here is that we push AF and then we push BC, but we have to pop BC before AF to make BC have the original values, because if we did it in the reverse order, BC would get the values of the original values of AF. And so if we first popped AF and then popped BC, then BC would be that 30XX and AF would be 0002 if we popped in this kind of order. So it goes always like this. So what you push first, you have to pop last. And what you push the second time, you have to pop the second last time. So if we want to push all the registers pairs on the stack, we have to push. It doesn't matter what order we push them as long as we pop them in the right order. If we do it like this, do some stuff with the registers and store values in RAM, for instance, and then we want to pop the registers we have to do it like this. Because if we do something else, the registers won't have the original values anymore. Although that can be convenient sometimes too, but normally you want to keep the register values, how to say it in English, unchanged. We push AF first, we pop it last. We push BC for second time, we pop BC second last time. Push DE third time, pop DE third last time. Push HL last, pop HL first. This is how you work with stack. So, stack pointer tells where the top of the stack is located, and stack is the memory area that is reserved for registers to be pushed there. And the whole stack area is between DF00 and DFFF. And the confusing thing about it is that the beginning of the stack is here in DFFF, and the end of the stack is in DF00. So it's like in reverse order. You would like to think it working to the other direction, but the beginning is the last address, and the the end of the stack is like the first address. Beginning is here, end is here. And well, yeah. This is how stack works and how stack pointer works. And like I said, you can push registers on the stack and pop registers from the stack. And along with those, for implementing subprograms with call instructions, we're actually also pushing registers on the stack. But instead of these registers, call instruction knows how to push BC on the stack. So the original program counter value is pushed on the stack, and return instruction is actually only used for popping BC from the stack. Because if you think about it, let's say that we have a subprogram at 27,4000, and stack pointer points to DFFF. Now that's not a rational. That's not possible. It can't point to DFFF if we are here in the game, really. Let's say the stack pointer points to DF D5. Yeah, this is the value of the stack pointer, and we want to call some routine subprogram. So we for example, well, if we are in this address, you can tell that program counter is 4000 because it's pointing to the instruction to be executed here. So first we have program counter as 4000 and stack pointer as D5. And actually, well, I'm making it like this, so it probably looks better. For example, we could already at the start call something here. We, for example, call routine like this, with this instruction, call 4120, and it calls stuff from this address. And after we do this, stack pointer is set to D3 because its stack pointer is decremented twice, and program counter is pushed on the stack. So in DFD3 we have that 4000 right now. And after it we have the original data starting at DFD5. Yeah, this is how stack works right now. We have 40, so original program counter value and all the other data in stack. And stack pointer points to DFD3 where the original program counter value was located. And for example here we push AF and push HL. Then we do some stuff, and we want to pop an AF, pop HL and pop AF. And after these instructions, stack pointer points to DFD3. After these pushes, it points to DFD3 -4, and when we pop those values back from stack, it points to DFD3 because, yeah, we push them and pop them. And if we, for example, now want to return from this subprogram, we can do it with return command. Or we could, for example, use return if chet flag is not set. And if it's set, for example, and A with A and then return. So if, for example, do something with A register if chet flag was not set during the operation code before this pop HL. But let's just say that this is just a return instruction, so we will always return from this subprogram after this pop AF is executed. So, well, I'll even put these as addresses here. So, in address 27, well, it works like this. And so let's just say that this code here is in address 27. Well, yeah. As you can see that these pop HL, pop AF, return, they don't have any parameters, so they have been programmed into the CPU with one instruction, one byte instruction. Call needs 2 parameters, so it's a 3-byte instruction, but this only takes 1 byte. Push AF or push HL. The register is actually not a parameter. It is. There are 4 different push codes. They all use a different hexadecimal presentation. Push AF, push HL, push DE, push BC. And same with pop codes. So we actually need 8 different instructions, such for register, push, and pop codes. Because we need 4 pop codes and 4 push codes. And return. Return now knows how to pop the value of program counter from the stack. So after this, stack pointer is incremented twice, so it points to DFD5, and program counter is set to 4000 because that was located in DFD3 in stack. And it's especially important that you do not modify the contents inside the stack. You only modify what is on the stack with the push and pop codes. but you do not do like something like you load. You shouldn't do something like this. Load df.do with a, because this is ridiculous. You should never do something like this, because now you're with this kind of code you're modifying something that is written in the stack, and when the stack pointer accesses this value, stack pointer wants to pop something from here. The results may not be wanted. Of course, someone could use this this as well, this could be a tricky way of doing something, and might be actually useful in some situation, but I can't think of a good way when you want to do something like this, really. But yeah, well, actually, I have a how to say it? I did something wrong here, because it actually doesn't take 4000 to the stack, because if we now pop PC with this return, PC is pointing to this call instruction in 274000. So actually how it goes is that before it actually before this address is executed, stack pointer is incremented thrice, because this instruction takes instruction and 2 parameters, so it's 3 parameters in total. So what we actually push to the stack is 4003, because now before we can push the value on the stack, the program counter is already pointing to the next instruction to be executed, which is after this call command, such as load BC with a. Load BC with value of a, or whatever it is. Yeah. So we actually were pushing 4003 on the stack. So here with the return code, it knows how to pop the pointer to the next instruction, which is this load BC with a. If we didn't, if this couldn't increment the program counter before accessing this address here, we would be doing infinite loop by always calling this data, returning, calling it again, returning, calling it again, and that way. That's an infinite loop, a loop that never ends. Well, yeah, that is how call command works. So it is a push. It's the same as a push command, but it actually pushes program counter, and then it, well, call is basically push PC, load PC with. This is what call command does. Pushes PC on the stack and loads PC with the address value that is attached to the call command as 2-byte parameter. This is call command. And along with call, we've got this errorstay. I don't really know how to spell that in English. But yeah, it actually does the same thing as call, but those are predefined instructions, such as we've got this push and pop instructions. We have call instructions for calling data from certain certain addresses with one instruction without parameters. So errorstay 08 is one instruction. This takes only 1 byte, and what it is, it calls data from start of the ROM at 0008. And the same thing could be written as call 0008, which is a 3-byte instruction, because the address here has to be attached as a 2-byte parameter. But yeah, this is what this code does. And you can attach different values to it: 0008, 10, 18, 20, 28, 30, and 38. And because these can be accessed so easily with just one instruction without parameters, games tend to use these addresses for storing some specific data. If you check out here, at the start of the ROM, you can see that we have jump to 827 here in 0008. In 0010, we have load A into FF00 plus 9F, and load A into 2000 and return. So we can access these two things with one instruction. And if you think about it, RST8, it calls this address, and here it actually jumps to this address. So what it really does, it calls actually this address what it jumps to. And if you check out what it does, it loads A into D156, loads this value into A, pushes AF register, loads the value in this RAM address into A. It calls data from start of the ROM at address 10 with RST10. Then it calls some other routine, loads value of B into A, and stores that into CFEO. Then it loads C into A and stores that into CFE1. So what this actually did here, it stored the value of BC into CFEO and CFE1. Then it pops BC from the stack, loads B into A, does RST10 again, and brings these values back to BC and returns. And this call here, it calls data from here. And we've got this kind of special instruction, jump HL. It jumps to, it sets the value of program counter to the value of the address of HL. So if HL holds 30 A5, that is put into program counter. So the next address to be executed is at 30 A5. That is jump HL. And this could be used with a thing called jump table. There are different kinds of tables. We have pointer tables. We can also build things like jump tables. But yeah, this is the basics of this program counter, stack pointer, stack, push, pop, call, RST, return. And we have different kinds of return codes, which I introduced the last time. And there is even RITE, which what it does, it returns and enables interrupts. And I'm not going to explain interrupts in this part. I don't even know that much about them, but I can explain the general idea behind them later on. But now, let's move on to tables, and actually take a little break before doing that, but Well, yeah, I'm back, and I'll actually clear this data here, so I have more room for writing data here. And well, yeah, tables. By now, I have already. Well, actually, I'll just start writing data here. But by now, I have already talked quite a lot about tables. You know that there are different kinds of tables in the games, just as the evolution data table. Well, all kinds of pointer tables are built in the HAG, and lot of other tables as well. And well, the thing is that a major part of the programming is actually having something to do with tables. And already here in the beginning, and at this address, well, I'm used to this, so I can see it. Well, already this here, this little code here, this is actually a code that uses a jump table. How it works is that it uses the value of register A. It first pushes DE on the stack, and in the end of it pops DE, so the value of DE will stay the same. And it uses register A for well, what it does, if we have A has the value of 0,4, it takes that 0,4 into E and loads D with 0,0, and then it adds DE into HL twice. And after this, HL has the value of HL has been increased by 4. And this is actually a way to say it, that HL as HL plus 0,4. That is the exact same thing, and most programming languages can be used to write like that. But well, if HL, well, I can show it like this, but I will soon enough. So let's just look for first look for that evolution data table in Pokemon Gold and Silver, and it was somewhere around here. I might actually run into it straight or not, but not 0x, but without it. 427 BD. Yeah, it is actually here. I do remember some of these addresses by heart, but yeah. This is the evolution data table is a pointer table where each let's see what it is. Each element of the table is 2-byte long value. So the first element is B369, the second element is CE69, and so on. And we have 251 elements in this table, because that is as much as the game really needs. And if HL, let's just see that let's assume that HL first, the value of HL is 67 BD. And if that is correct, it points here. And A has the value of 0,4. Then if we use errorstay28 instruction, we start calling data here. And this pushes the value of DE, loads A into E, and loads 00 into D. And then it adds DE to HL twice. And then we have HL set to 67 BD plus 04 plus 04. And this is D plus 3 is 0, and we add 5 to that, so it's 67 C5. HL is set to 67 C5. And if we think about it, this table here, the first element is in 427 BD, and the pointer to this address is 67 BD in Big Indian format. And let's think about the pointer as the value of HL. To the next element, it is 67 BF, third 67 C1, fourth 67 C3, and the fifth element is in 67 C5. And that is what HL is now pointing to. So we can see that when we had value of A as 0,4, that A actually refers to the fifth element in this table. And if A was actually 0,3, it would have referred to the fourth element of this table. If A was 0B, that would have referred to 0C or 12th element of this table. Because each element is 2 bytes long, and we add the value of A twice. We're adding A because D is set to 00 and E is set to A. So we add A twice to HL. So with A being 0,4, we can point to fifth element of this table. And these codes here, let's think about what they do. In this case, HL is set to 427 C5. LDI A with HL is an instruction that loads the value in this address into register A and then increments HL. Increments the address of HL. So A is the value here, which happens to be 7C5, it is 24. And then HL is incremented, so HL is 67C6. Because this is both. It loads the value of HL into A and then increments register pair HL. And then this instruction, it loads the value in the value pointed by HL. So the value in ROM address 67C6 into register H. And this may seem confusing, but now H is set to 67C6. And if you think about it, this of course affects the value of HL, because HL is formed with H and L. But now H is set to, we load the value of HL into H and that is the value from this address, which is 6A. So 6A is put to H, and after this HL is 6A C6, because L is still C6, like here. We only load we only modify H and L stays the same. And next instruction is load L with A. And after that instruction, L gets the value of 24 because we bring this into L. And then HL is 6A24. And then we pop DE and jump into HL. And the only problem with this code used in this kind of situation is that we don't want to jump to HL. But what this 6A24 really is? Well, HL now holds the value. Well, first HL, in the beginning of the code, HL holded the pointer to this pointer table. So HL pointed here. Then we had the index -1, because in this case we're referring to fifth element. So this is index -1. The index we're pointing to, -1, is in register A. And then with by adding DE to HL twice after doing this, HL is set to the address where the referred pointer is located. And then with these three commands, load and increment HL into A, load value of HL into H, load A into L. HL is actually, from the address, we actually bring the value of that address into HL. HL first holds this address. After these three instructions, HL holds the value of this address. And now you can probably also see why this thing here is in Little Indian format. If this was 6A24, after these three instructions, HL was 24-6A. So we want to make them, we want to put them in this backwards order, because if we didn't, we couldn't easily load HL with the value in that address. I don't think there is any other instruction set as simple as this one that could do that. And then we pop DE, which we pushed earlier, and we could jump to that address if this was a jump table, because you can also use tables as jump tables. And here is a pointer table. So we have a certain code that uses this. And let's just track it down. So the pointer table is in 427 BD. 7 BD. I input that here. Go to the start of the ROM bank and search for those bytes. So BD67, yeah. And here you can see we are loading HL with 67 BD. And this instruction set here isn't much different than what I went through just a minute ago. The index of the table is in DO D3. We decrement that index here. Index -1 is in A. We load BC. We load B with 0, 0 and the value of A into C. And in that other example we did the same thing with DE. Now we do that with BC. We load HL with the start of the pointer table, add BC twice, and then do this. Load load and increment A with HL, load A with HL, and load A into L. And now, if this value first was 0.5, it was decremented into a 0.4, and this was done. So right here, after this instruction, HL is 60A24. Then we push 60A24 on the stack, start doing some stuff here. Then we pop that 60A24 from stack. And the code that follows it, well, let's check that out too, for fun. It points here in 420A24, which is right here. You can see that we have this. Well, this is, yeah, it was the 5th index. Well, it was the 5th index, so it is of course Charmeleon's data. Should have known. We have 0.1 for making Charmeleon evolve at level 24 into 0.6, which is Charizard, and no more evolutions. And then we start doing stuff with this code here. With this code here uses this data for doing stuff. We first bring the value of HL into register A and increment HL. So HL points here and A gets the value of 0.1. We AND A with itself, and AND operation works so that when you AND it with itself, you get the result back. And A with A brings A. But 0 flag is set if A was 0. So this actually is checking whether it's actually just for checking whether this Pokemon can evolve or not. If it's not 0.1, if it's not 0.0, this Pokemon can evolve. Then we load that value 0.1 into register B and compare A with 0.3, which is evolution method happiness, I think. Then we check whether the evolution is happiness evolution. Compare A with 0.3 sets 0 flag if A is 0.3. And if this is happiness evolution, we start executing data here. Program counter is set to 61 to B1. Then we load value of DO42 into A and it with self, and jump here if 0 flag was not set. And what could this mean? I can't pick that up right now. This is also some evolution method, some sort of. Next we brought that value 0.1 into B. We load it from B back to A. So now A has still that 0.1. And HL was incremented here, so HL points here to 24. Then we check if the evolution method is stone evolution. And if it is, we jump to 62 D8. Then we do stuff such as this again. I don't know what for. And again, load the evolution method into A. Then we check if it's 0.1, and in this case it equals, and we jump to 1062 F1. Then we load and increment A with HL. HL points to 0.6 and 24 is set to register A. We bring that 24 into register B and bring the value of DO20A into EA and compare them with each other. And this actually here now, it holds the current level of this Pokemon, most likely, very likely. And then we check if the current level equals to Well, the evolution level is now in register B, and the current level of this Pokemon is in this address, which is brought into A. We compare them with each other, and C flag is set. I think C flag is set if the result was smaller than 0. So in this case, if A was smaller than B, C flag was set, and A smaller than B, C flag is set. I have to think about it. Which does B? B hold this value, and the current level is in A. Yeah, if A minus B is smaller than 0, then we jump here, and this thing tells that our Pokemon is underleveled, or not. It hasn't reached level 24 yet. If it has reached, it starts doing stuff and making it possible to evolve. This thing here used for printing text data. I'll just let you see that too. We load HL with the text data pointer, which is here. Wait. Is this correct? Well, I don't know. This may be somehow modified during the code or such. But, well, yeah. This is how you work with tables. I'll introduce you to some other table as well by writing the code here. So we've got the RAM map for Pokemon Gold here, and the game settings under here. We have the item pocket stored in RAM. Total item count, item number 1 amount, item number 2 amount, item number 3 amount, and so on. And this is a table too. It's a table stored in RAM, in which each element is 2 bytes long. Each element, the first 8 bits of that element is the item number, and the following 8 bits is the amount of that item in the pocket. So we have a 20 item long 20 elements long table in RAM for storing items that are in your pocket. And if you check it here, D1, B7. Well, yeah, now we don't have any items in our pocket, but let's just go to the gameplay so I can show you. The pack works so that it shows the amount of. It shows all the items before cancel, and cancel is loaded with this FF here. So total item count is in D5B7. So if we change this to 0.5, it acts like we have 0.5 different items in our pocket, and I can actually scroll up to 5. 1, 2, 3, 4, 5. And this here is cancel, and I can't scroll any longer. And if I put stuff here, do I now have 5 items? 1, 2, 3, 4. No. Now I have 5 items in our pocket. In the pocket. We have number 13 5 times, number 14 5 times, number 11 0x 50 times, number 12 1 time, and number 17 1 time. And can FF for indicating cancel here. If we don't have cancel, we can scroll. We can scroll further because this byte here actually tells how far we can scroll in the pocket, but we see this instead of cancel because FF is not there. And now I put FF there, so item pocket works fine. But, well, yeah, this is a table, and you can see how it works. We have the actual table starts here in D5B8, and it works so that we have 2 bytes for each element in the table. Item number, amount, item number, amount. And the table ends. Table is restricted with byte FF. So where we have FF, that's where the table ends. And I'll build a certain code for checking whether we have. Let's build a code for checking whether we have escape rope in our pocket or not. And escape rope is item number 13. We know that the item, the amount of items, well, the items are stored starting at here, and the item pocket, well, the table ends at FF. And if we, for example, have 13 here, this doesn't indicate we have an escape rope, because we have just 19 amount of repels. We have 19 repels, we don't have escape rope if 13 is in this slot, for instance. So it all has to be in slot D1B8 plus 2 plus 2 plus 2 plus 2 and so on, somewhere before FF. And this kind of checks are quite useful and used in the game a lot, very often. And we actually wouldn't have to build this by hand because there are lots of routines in the ROM Bank 0 for doing stuff like this. So you just have to track them down. I don't have them. I don't have many written down in my PC, so I can't really share much. But I can show you how this works. So we could start off by, like with other table checkings, we could start off by checking. Well, let's start off by loading HL with the start of the table. And well, let's not. In this example, I'm checking if escape rope is in the pack, but let's start off by let's do so that let's write a subroutine that it sets carry flag if the item is in the if its value of register A does the value of register A belong to a restricted table. So we, for example, we load A with that 13, which indicates for checking if escape rope is in the pack or not, and we ignore the amount bytes here because we don't want to set carry flag if you have 19 repels. We only want to set carry flag if we have at least one escape rope. So we load A with 13 and call routine. Let's just say that this routine is in address, this address, and we're still in that ROM bank. Yeah. And we set carry flag is if one item in the at least one item in the pocket is this item number 13. And here we, for example, if carry flag is set, we jump to some routine carry set, and if not set, we do stuff. But I'm not going to fill anything here. I'll just fill this check whether or not we have escape rope in the pocket or not. So A is loaded to 13, then we call some routine, and what we want to do, well, let's just do it. Let's push all the registers at first. Push registers, and later on we pop them. And return. And before this, carry flag is either set or reset. And after we have pushed the registers, we load HL with D5B8. And then we could, for example, load DE with 0002, because we're checking every second byte of this FF array table. So the table ends with FF, we know this. And then we could load. We really don't have to do it like this. I'm doing it another way. Or Actually, I want to do it like this. Yeah. I want to preserve the value 13 in register A during this routine. So we load this into HL and this into DE, and we already want to check if the value in D5B8 is 13, because D5B8 is the first item, 2 bytes ahead we have the second item, 2 bytes ahead the third item, and so on. Now in this case, I'm assuming that this byte is FF, so that we actually won't be checking whether 13 is in key items or in ball pocket or in a stored item or such. Yeah. So we do this, and then we, for example, I think compare function, a compare instruction allows us to compare A with value in HL, if I'm right. Yeah. A minus 1 subtraction, but results are thrown away. Okay, so we compare A with the value in HL, and if 0 flag is set, we let's just say it sets 0 flag in this case. And if we have that item, it jumps to item 13 in pocket. It sets 0 flag. Well, this instruction sets 0 flag if A matches with the value in HL. In this case, we jump to 6550 for ending the routine. So if the first item is 13, the routine ends. If not, we add DE into HL for checking the second item. No, not yet. Well, I'm renaming this as, because this is in 5600, 01, 02, 03. This next instruction is in 275604. So I can explain this better here. So here we would jump back to actually we want to do these here already. This takes 3 bytes, this takes 3 bytes, so this is actually in 560A, the next instruction. So we do a loop here where we compare the value of A and the value in address of HL. Then if those match, we return from the routine and 0 flag is eventually set. 0 flag is set here and the routine ends. And well, actually right now we also want to check if this how to do this better. I have to use A for comparing, so I, for example, load A into register B and load A with the value of HL for checking whether this value equals to FF. Yeah, I want to do that. If A is FF, we return from this routine. XOR instruction sets the 0 flag. So I want to do it like this. So I XOR A with itself for resetting 0 flag, which was set here, and end the routine. If we are checking, if we see that A matches with FF. Otherwise, we do it like this. There are probably a lot better ways for doing this. This simple routine here too. But with what it does now, it checks if certain index value in this table matches with the value of A that was given to A when calling this routine. If those match, it jumps here, ends the routine, and does this. Otherwise, we load A into B and bring the value in HL into A for checking if that value is FF. So if we have reached the end of this FF array table? If so, we reset 0 flag, pop the register values from stack, and we didn't have the item in the pocket. And next, if that value didn't match with FF, we still have more slots to be checked, so we add DE to HL, which is something which could be, in this case, D5 C2, turning to D5 C4, wherever this HL is. It is incremented twice. Yeah, I don't really need this. I can just increment HL twice, so we don't even need DE during this operation code. As you can see, this now changes into 5608 and this into 5608, and it works. Well, now we don't need BC. Now we don't need DE in this code at all. This is better. Yeah. Now this start here takes 6 bytes, and this code follows it. And we go through this loop again, over and over again, until the value of HL matches to FF, or it matches with the given value of A, which is checked here. And then we check it again. And finally, the routine ends by either resetting 0 flag, in this case, or not resetting the 0 flag. And we pop the registers, and we return here by popping program counter. Like I explained, that return does that. And then we do something if we had that item. We could, for example, store that value somewhere in RAM, like D004, where we could store values, and then through a script do something related to having the escape rope in our pocket. And I'm actually even using a similar thing in my own hack. Well, yeah, you can just check item. Yeah, there's check item code for checking if you have certain item in the pocket, but if there was no check item code, you could do it like this. And well, yeah, this is how you can check this. Well, this is one possible way of checking if you have a certain item in your pocket or not, and it could be optimized a little better than I'm doing here, but this works. And well, I guess these may actually wait for better occasions if I'm going to talk about them more or not. But I'll just let you see how you can copy data. That shouldn't take too long. It's actually pretty easy way to do that. So, copying data, it works by well, this time I'm assuming we don't have to push or pop anything, but we can always do that. We can push first and then pop at the end of the code. But you call some copying routine. First, you load HL with source. So the pointer to the where you want to copy data, load DE with destination, yeah, and BC with length of data to copy, and this is one possible way of doing this. There are of course infinite amount of ways for even doing this kind of job, but I'm just showing one way of doing that. And then with these values, if you do this by calling an assembly data assembly script to through a script data, you can just jump to the copying routine, whatever you have it as, or again, the original game does have a copying routine in the ROM bank 0, and I don't remember the address by heart, but it is there, and it's a bit different from what I'm going to introduce. But we can just jump to the copying routine if we are calling assembly script through game scripting engine, or with it. And the copying routine, it could work like this. We actually go through this thing as a loop, so that every time we bring the value from the destination to source, and we increment the source and increment destination, so that, and then we decrement length, and then we check if length is 0. If it's not, we do the same thing again. Increment source, load value from destination to source, increment source, increment destination, decrement length, and that way you can move data from place to another. So let's see. We want to load the value from destination into register A, and then we wait. Now I'm saying this wrong in English. This is better. We bring the value from source to destination, of course, and then we increment both of them. So we load value from source to destination, increment both, and then we decrement length. And next we check if length is 0, and there are many possible ways of doing this, of which the most simple way to understand would probably be loading both values. We could, for example, do it like this, or I'll just write it in a. Well, this is like a stupid way to write this, because this is no way optimized code right now, but we compare the value of B to 0. If it's not 0, we jump to copying routine, and then we load the value of C to A, also compare that to 0, 0. And of course there has to be a check. If 0 flag is not set, we jump to copying routine. And if both of these are 0, the copying is complete and we can return. And this could be built with a lot better way. For example, we could use load and increment here, and then load the value into DE. So we don't have to increment HL here. We can do it like this, and then decrement BC. And here was some trick you can do all this at once. Yeah, you could load the value of C into register A, and then OR A with B, and now if result is not 0, we jump to copying routine. What this here does, well, yeah, A gets the value of C, and then we OR A with B, and jet flag is set if A register turned into 0, 0. And if you OR two values together, the result is 0, 0 only if both of them are 0, 0. So with two instructions, we can change these 5 instructions into 2 instructions like this. Although it may not be so user-friendly to look at first, but this is now optimized code of this copying routine that I wrote before, and it works the exact same way. It has to execute less instructions than before. We built these two together, and this here was written with 2 instructions like this. And this copying routine is very useful actually, because well, anyway, anytime you want to copy code from place to another, you can use a routine like this. This thing here works just fine, and if you want, we could call the copying routine, and then this uses all the registers, so we can no, wait a second. Now this is kind of tricky actually. Yeah, we want to push them before. If we don't worry about A and F register, we can leave it unpushed. But this time we actually want to push these registers before and then load them with the values. And after the copying routine, for stack to work properly, now we have to pop them in the reversed order. And now copying routine works. Now the way we call this routine works. We push the registers, load the right values, call the copying routine, and pop the registers, and do stuff here, whatever we want to do. If we care about the registers, that is. Well, yeah. That is one example of building a copying routine in the game. And there is already a copying routine in ROM bank 0. So you really don't have to build anything like this there though. And well, yeah, the rest may wait until next time, and I actually explained the subprograms somewhat already. There is really nothing more to it than just pushing register pairs in right order and that kind of stuff. And if you well, I'll show this kind of example. If we you can't do like this. This doesn't work. Push BC, call routine, and inside the routine pop BC, because now BC gets the value of program counter, well, that was pushed. Here it pushes program counter, so BC gets the value of program counter if we pop BC here. And now if we, for example, return from this code, then program counter gets the original value of BC that was pushed here. And this can lead into computation errors and that kind of stuff. And you have probably seen a thing called Invalid Opcode. Especially in those Game Shark videos people keep posting in YouTube it over and over again, where they walk through walls and crash in the wall and that kind of stuff. And this Invalid Opcode is actually an error of the CPU trying to perform a machine instruction that which opcode is not defined, because all opcodes are defined. Call is CD, NOP is 00, load, where there are many load codes, for example load A with 3E, I think this is E50, this is 3E50, and so on. And there are lots of opcodes that are unused. I can't tell them by hand, but for example some E7 may not be used, or F8. So if the program counter somehow gets to the data area, for example RAM, if PC first points to RAM, then we pop these in wrong order, PC gets the RAM address in it and tries to execute data as machine instructions there. It can work for some time, and well, of course it doesn't do anything wanted if it works, but it will work for some time until it tries to execute an opcode that is invalid. And then this is actually an interrupt. This is now an interrupt. And the CPU gives an error report or interrupt, and an interrupt handler stops executing a process, and you get this invalid opcode error message with VBA if you try to do something like that. You can try it out, and especially if you can check the debugging functions with BGB emulator that I'll be showing off next time, and see how it works if you try to crash in the wall and start debugging and see what the processor is trying to execute. It can work for some time and execute something very stupid at it. And when it hits an invalid opcode, it gives this error report. At least so I think it does. I haven't really checked it out myself. But yeah, that is pretty much all about subprograms. You have to know how to push registers in the right order and pop them in the right order. Call is push PC and load PC with the value of this routine here. So push BC call routine. Well, this is just push PC load PC with address, and then do stuff. So we have to, of course, pop PC first, and this works with return, and then we can pop BC. You can't modify PC with just normal machine instructions or these push pop instructions, but there are return and that kind of return, call, jump, relative jump that can modify it. And stack pointer can also be modified by hand, and that works with load HL with stack pointer and load SP with HL, and there are some other codes as well, I think. I'm not totally sure about these either, but I think these two instructions exist in the Gameboy CPU. But yeah, I'll be showing some in-game routines next time, maybe tracking down some of them, like checking how you can track down the routine used for making it possible to use fly or not if you have the Signwood gym badge, and so on. I'll also show you Lin's assembler tool, and I might stop posting these videos next time, or upload part 10 and maybe even part 11. I don't know, but I'm not that into this kind of stuff myself either, that I could explain more than I have already explained, I think. So yeah, there's not much to be explained anymore, really. You can study the high RAM area on your own and how the input and output registers work and that kind of stuff of RAM. But I'll introduce you the assembler, BGB emulator, and its debugging functions, and debug some routines, and tell something about interrupts that I don't understand that clearly myself either. But that's all about it for now, and see you then.